Welcome back. This is AP Environmental Science, Chapter 2, Part 2. And today we're going to learn about some properties of water. Don't forget to review the different, like we were talking about last time, the different chemical bonds, covalent, ionic bonds, etc. In your book. Don't forget to memorize some of those definitions and such and review your basic chemistry. So we're going to talk about the properties of water, and it's these unique properties of water that make life abundant here on Earth. The fact that water is in its liquid form on Earth at most places on Earth is one of the reasons why life is abundant. So we're going to talk about some of the properties. So the first property that we'll talk about is the surface tension. So water has a unique ability to stick to itself and then also to other surfaces or other molecules. And so water has a high surface tension, and this is just cohesion of water molecules, so its ability to stick to itself. It also has what we call capillary action, and this is its ability to stick to other molecules. And so this is called adhesion, its ability to adhere to other molecules. Capillary action can be seen in plants through the xylem cells. So if you remember back in biology, we talked about xylem cells in water moving from the roots to its leaves. Also, we can see this in groundwater. As groundwater moves through the soil, it's through capillary action that this takes place. So here's a water strider. The water strider is able to sort of walk on the surface of the water because of this high surface tension that water has. And so you can see it just, instead of sinking through, the hydrogen bonds between water molecules enable it to sort of glide on the surface of the water. Water also has a high boiling point and freezing point, so it has unique properties in boiling and freezing points. So water boils at 100 degrees Celsius and it freezes at 0 degrees Celsius. This is important because if water boiled at a much lower temperature, then in most places on the Earth's surface, it wouldn't be a liquid, but rather would be a gas. So it's important that water has a high boiling point. That way it stays as a liquid state in most places on Earth. Water also is a great solvent, and so it is a polar molecule. Water is a polar molecule, and this enables it to bond easily with other polar molecules and dissolve many substances in water. A very unique property of water is the fact that as it cools, it becomes less dense, and so water has the ability to float. And so liquid water, if you see here liquid, it's quite dense. They're all closely packed together. And as it cools, it gets more and more dense up until a point, until about 4 degrees Celsius. It's hard to write with this tool, I apologize. I'm trying to get better tools to draw with, but at 4 degrees Celsius, it's at its maximum density. As it continues to cool down to 0 degrees Celsius and beyond, what happens is it increases in volume, and so you get this structure, this crystal structure. And so the volume increases. The volume increases, this makes it less dense. And so what you have here is solid water or ice is less dense than liquid water. And so therefore it floats on top of liquid water. And so this is a unique and important property of water. Acids and bases, when you dissolve a substance in water, if it contributes hydrogen ions or H+, again, sorry, it's hard to draw with this. So H+ ions, hydrogen ions, then it's an acid. The more H+ you have, the more acidic it is. If a substance is dissolved in water and it produces hydroxide ions or OH-, then it's a base. The more hydroxide ions it has, the more basic the solution is. This is the pH scale, which I'm sure you're familiar with. At 7, it is neutral, and that's pure water. At pH 14, it's most basic, and that's something like sodium hydroxide. We'll be using sodium hydroxide in a biofuels conversion lab. At pH 0, it's the most acidic, and so here's some examples of very acidic things like stomach fluid or soda. Lakes that are affected by acid rain can be quite acidic, between 3 and 4 pH. Normal rainwater is slightly acidic, between 5 and 6 pH. Seawater is actually basic. It's near pH 8, but seawater is decreasing in pH and becoming more acidic. This is due to increased CO2 levels in the atmosphere. CO2 is dissolved into the seawater and then becomes carbonic acid. So the more CO2, the more carbonic acid, and then the more acidic the seawater gets. We'll be talking about this more later. So understand the pH scale. And pH indicates the strength of acids and bases. So chemical reactions and conservation of matter. So chemical reaction is just the rearrangement of atoms. So atoms separate and they recombine with other molecules. And so chemical reactions you're not losing anything, you're just rearranging it. This is a very, very important concept here. It's the law of conservation of matter. And so law of conservation of matter is important in all science, but particularly in environmental science. We'll be talking a lot about this. So matter cannot be created nor destroyed. And so when you have a chemical reaction take place, none of that matter is destroyed or created. Rather, it's just a rearrangement of atoms and that matter. And so down here we have a gasoline combustion reaction, where you're taking gasoline, you're mixing it with oxygen, you have a little spark here, and then you get CO2 and H2O or water. And so the reactants on this side, the matter that composes the reaction or reactants, is the same amount of matter that you get on the product side. So it's the law of conservation of matter. Nothing's created or destroyed in that reaction. If you look at a forest fire, the same thing. Forest fire goes through, you see what seems to be matter destroyed and disappear, but rather what's really happening is it's just forming new molecules and moving to different areas and such. And so the fire may convert the forest to ash, ash on the ground, or also solid particulate matter that floats into the air, and that's called smoke. It's hard to see my blue pin here, but smoke goes into the air and travels somewhere else. So again, law of conservation of matter. None of that matter is created nor destroyed. It just moves and is in different forms now. Not going to talk a whole lot about this, but inorganic compounds, you should know what this is. It does not contain carbon, and if it does, it's not bound to another carbon or a hydrogen. And so carbon dioxide is a inorganic compound, and all of these are inorganic compounds. Organic compounds, you're looking at a carbon-carbon bond and or a carbon-hydrogen bond. And so here we have glucose, over here we have methane. Just remember back and memorize these definitions: carbohydrates, proteins, nucleic acids, lipids. Cells, again, smallest structural and functional component of organisms. We have single-celled organisms, and we also have multicellular. Here's single-cell organisms, here's a multicellular. This is brine shrimp. We'll be doing an experiment with brine shrimp later. And so now we're moving on to this concept of energy and energy use and all sorts of things. So energy, this is a very, very important concept, because in environmental science, energy is key and central. So energy is a fundamental component of environmental systems. So understanding energy, how it flows, and as much as we can understand about energy in a system, it is absolutely crucial for our understanding of environmental science. So we'll be talking a lot about energy. So energy is just the ability to do work or transfer heat. The units that we'll be talking about, the SI units that we use, are joules. So we'll be talking a lot about joules. We also have other important equations, mathematical equations and relationships that we'll be talking about. And so here's one, but power is the rate at which work is done, and we'll be working with a lot of these in lab, so we'll get familiar with these equations. Table 2.1 is a very important table, so you should take a look at this. Over here we have units, and so you should know those units, also the definition of those units, and then the relationship to joules. So remember, little c calorie is different from big C calorie, and you should know that, what it's talking about. A BTU is something that you may have heard of before when you go and purchase a barbecue or something, and please know the conversion. And then a kilowatt hour over here is something that we'll be using often, very, very often. So know the conversion, know what it is, kilowatt hour, get used to those, very important. So forms of energy. There's kinetic energy, that's energy of motion. You have potential energy, that's energy that is stored. Chemical energy is a potential energy, and it's the energy stored in chemical bonds. And so when you break these bonds and rearrange them, you can harness some of that energy. We'll be talking about this when we talk about electricity generation. When we talk about temperature, what we're talking about is, well, it's a measure of the average kinetic energy of a substance. So the faster the molecules move, the higher the temperature. So when you take water at room temperature and you heat it up, really what has happened is, yes, there's an increase of temperature, but all that is a measurement of the rate at which molecules are moving. They're moving much faster, and so it's a higher average kinetic energy, and so therefore a higher temperature. What you have here is a dam, and we'll be talking about hydroelectric power plants. We'll be talking about the pros and cons. It's oftentimes viewed as clean energy, but it's only clean in certain ways. It also has cons. But on this side of it, we have potential energy. That's the water behind the dam not moving very much. And then here we have kinetic energy. We harness the kinetic energy to bring power to your homes. So that's the end of part 2, and we'll continue to part 3, the last part of chapter 2. We'll be talking about the laws of thermodynamics in this next part. So that's the end.